Good morning. My name's Alan Mickelson. I'm a professor at the University of Colorado, and today I'm going to talk to you about silicon photonics. Let's start with talking about where silicon photonics is today, or at least what it looks like today. Here's what I call integration by functional island. Over here, we have an optical module, which I'll go into a little bit more in a minute. But what we're doing here is we're using optical modules together on a package to hook together ASICs, FPGAs, GPUs, other electronic components. So when I talk about photonic CMOS integration, it's happening. These packages exist. We'll see them as we go along, and they're progressing. They're becoming more integrated. People are putting them devices closer and closer together, and they're going to higher and higher bit rates. And this optical modulator, when we break it out, is going to have CMOS drivers, but someplace underneath here, there's going to be a silicon photonic chip, most likely. So we have lasers over here, DFB lasers that are indium phosphide. We're going to have silicon photonics with modulators, photodetectors, and waveguides. And we're going to have fibers, and those fibers are going to take the light away, driven by CMOS. So this is a picture of what things look like. Looking at optical modulators on interposers, we call these optical modulators now interposers, the idea being that we have a layout on here, a silicon photonic chip. We have transimpedance amplifiers, we have drivers, we have other things that are hooked to a ceramic perhaps ceramic or other kind of substrate. And that the silicon photonics here, what it consists of, we see are all kinds of devices on here, modulators, and we see that we've got couplers for demultiplexing and multiplexing on top of this device. And this is what these look like. These are actual physical layouts of what they look like, where we're talking about, again, an interposer package. We talk about interposer packages, and oftentimes these interposer packages have ball grid arrays hooking them to some kind of board. Okay, so I'm starting from somewhat from the end. I'm saying that for many years, we've been doing system on chip, we've been doing system in package, we've been doing system on board. What silicon photonics is now doing is it's becoming one of the elements of these various packaging technologies. So we're starting from the end. We're going to have to go back and work a little bit forward, and then we'll work a little bit into the future from here. But this is pretty much where we are. We're now moving silicon photonics into the board level CMOS interconnects. So to summarize that, let me move over my picture here a little bit. So photonic CMOS integration today consists of functional islands on interposers. Photonic integrated circuits have external sources and drivers. However, all of the modulators and all of the detectors are on these photonic integrated circuits. And the interposed optics is an additional element in traditional electronic packages. And this is where photonic CMOS integration is going. This is really where silicon photonics is going in the future. Let's take a look a little bit at where silicon photonics has been and where it's, well, later we'll look at where it's going. This is the silicon photonic market. So part of this is past, part of this is future. Indeed, this was a projection at the time, but that projection has pretty much come true. It's a little bit hard on whether this is only transceivers or all silicon photonics. But at any rate, from 2014, the market grew at a rate of about 100% compound annual growth rate. Since then, since about 2017, it's been growing at 25% compound annual growth rate. And silicon photonics went from being essentially not a market at all in 2010 and still pretty much an infinitesimal market by 2013. It's now a multi-billion-dollar market. It's a very big deal. This is up there with fiber markets and laser markets and whatever on the scheme of photonics, on the scheme of electronics. Along with this growth in the market, we've seen quite a growth in complexity. In the early days, silicon photonics might have a couple of components on a substrate. That would be it. But it's been growing exponentially ever since. There's a different growth rate for non-transceiver products than for transceiver products. The vast majority of products that are on the market now are these transceiver products. And we can see they're growing at a healthy exponential rate. And transceivers now, if we look over here, have hundreds, literally hundreds of components, 200-300 components, primarily WDM components. There are other components up here, other chips that have up to 10,000 components. We'll see at least one of them, which is a 50 to 50, 50 by 50 crossbar switch. This was all the way back in 2017, a paper by Michael Hochberg and group at that time. Well, now that we've said how much silicon photonics sells and how expensive it is and where it goes in circuits, maybe it's time that we should define what silicon photonics actually is. And what silicon photonics is a waveguide, however, electro-optic waveguide based circuits. They are fabricated on silicon on insulator wafers, which are diced into silicon on insulator chips. And now, if you're going to have 10,000 components on a single chip, where that chip may be a few square millimeters, it requires CMOS processing. It requires CMOS processing not just for the waveguides. It requires CMOS processing because those modulators require PN junctions, detectors require germanium implants, and these can be very complicated things to do with nanometric masks in a usual lab. If we look, this is what a silicon wafer or a silicon on insulator wafer looks like. You've got a thin top layer of silicon, you have baried oxide, a couple of microns, and then you've got base silicon. This base silicon is, as we'll say, 600 microns to a millimeter. So that's what silicon photonics is. Let's go back and talk a little bit about CMOS design flow, or talk a little bit about why this requires foundry fabrication. This is from Luceda. Luceda is a company, Luceda Photonics, which is in Ghent in Belgium. It's near the main foundry, the Inter-University Microelectronics Consortium of Europe, which is in Leuven, Belgium, which is near Ghent. Luceda Photonics was formed by many of the people who built the original line at IMEC, this Inter-University Microelectronics Consortium, IMEC. They had the first commercial foundry that took in anybody's designs. That goes all the way back to around 2005. And this here is what they say is a design flow. You come up with an idea, then so far silicon photonics doesn't have what we call hardware definition languages. If you're doing circuit design, you actually have a hardware definition language. Silicon photonics hasn't actually come that far yet, but very rapidly you can go to circuit capture and simulation. So you come up with an idea, you lay out some kind of circuit, you can start simulating it, you can start optimizing that circuit. You come down here along the design flow, you can do layouts, you can then physically simulate the layout. You can do design rule checks then. This is all now using graphics, the same graphics that we are the same design software that we're using for CMOS design, things like Mentor graphics and Cadence. We can do layout, design rule check. We can do functional verification. And then after fabrication, we can do testing. And at this point, as we'll talk about as we go along, testing also is pretty much becoming something that need be done at a foundry. So design flow, this is actually a layout. This is an early one that we did. This is our layout from Guided Wave Optics Laboratory at University of Colorado Boulder. What this is a ghostwriter picture of a GDSII layout. The GDSII is a way for writing, essentially here was a 90 nanometer rule foundry. So this is a lot of 90 nanometer dots put together to form waveguides. And it was done, this is a small piece. There aren't dimensions on here, but this is a small piece, a few millimeters by a few millimeters of a layout on a 200 centimeter or 200 millimeter wafer. There are grating couplers on here at this end that you put light into to couple into the waveguides. They're grating couplers at the output. The waveguides in here, the channels that are along here are 450 nanometers wide. They are etch steps that are 220 nanometers. That's the red. The white is the silicon oxide. The red is the silicon, and these pedestals that are standing up 220 nanometers high. And this, I think, is then it says here it's 5 millimeters long. So at any rate, this is a layout that we do. Again, this would be very hard to do in a laboratory. It's something that's done in a foundry. Here's one of our wafers, a silicon on insulator wafer. Most of the ones that are used with photonics are still 200 millimeter. However, there's silicon on insulators also has a number of other uses, among them MEMS and also microwave RF type uses. There they use 300 millimeter. Photonics has been 200 millimeter, but I like this picture so much. It's so shiny. This was not made in my lab. This was from one of the foundries. This is from a Soitec foundry. Soitec came up with the process to write these silicon on insulator wafers. And this is Soitec. I do believe this is Soitec, or at least it's Soitec process. These are the wafers that you can choose from. Again, there are wafers, SOI wafers for power electronics, for RF, they're for imaging electronics, and over here they're for photonics, and this is somewhat, the bottom isn't drawn to scale, this is somewhat to scale. The Soitec wafer is a 220 nanometer silicon layer. It's on a 2 micron buried oxide, and here it's on a 300 millimeter, we saw on the last one, wafer, and that wafer is generally either 600 microns or 1 millimeter thick. The process by which you put these together is called a Soitec process. Generally, there's some wafer bonding where you wafer bond on the oxide onto the Czochralski silicon. silicon substrate over here. And this is very pure epitaxial silicon dioxide or silicon that goes on the top. Here's what we make with those chips after we dice up that 200 millimeter wafer. This here is a transceiver. Evidently, this one's from NEC. At one point, there were 23 companies making transceivers. NEC was just one of them. I just took this picture because it was a nice picture of the full package. And this is a PowerPoint of what goes in that package, what was in that package at the time. They're essentially 4 lasers, and those 4 lasers are coupled to a silicon photonic chip, which has multiplexers, modulators. Actually, here it doesn't even have multiplexers. Here it just has modulators, and it has detectors, waveguides and detectors on the other end. And we have drivers, electronic drivers, and we have electronic transimpedance amplifiers over here that bring in the electrical signal. This plugs in to a data center, plugs into a gigabit Ethernet card. And over here, we can see electrical contacts. The drivers are inside the package. The signals come in, get amplified to the drivers, and they come back out on the other side. And out here is where an optical fiber will likely pop out. Modulators and detectors then are on a silicon photonic chip. Everything else is packaged. So there's a very tiny little board that goes inside of here. This thing here fits in the palm of your hand very easily. And again, it plugs right in plugs into a rack, into a thing with many, many plugs. We'll see more on that as we go along. If we look, here's a blow up of what actually is in the SIP wafer. This here is a layout. This was done in my lab. Here we were laying out one of the first transceivers that we were making. So what we have here is we broke it out into 2 separate silicon photonic SIP chips. There's a SIP chip over here that's 7.5 by 1.2 millimeters. It's pretty small. It has connectors going to a laser package. Here we did have de-muxers and muxers. We split out a comb into 4 different channels, and we put them together into a connector, which then goes out into a fiber. Over here, we have 4 detectors. Again, these modulators, demultiplexers are on the silicon photonic chip. The modulators require doping. They require PN junctions. So these, and they also require electrodes that are driven off the driver. The detectors also have electrodes and require germanium implants. So this is silicon photonics, and this is how it fits into an electronic package. This is a SIP modulator. The modulator is rather long, so I wasn't able with the camera. This is one that we made at the Inter-University Microelectronics Lab in Singapore. This one over here then, so this has a very high aspect ratio. This is what the input of the waveguide looks like on an SEM. This is a picture looking down on the top of the electrodes. And this whole device is something like 5 millimeters by, this is something like 100 microns in this dimension, would be this picture. These are all test structures. The modulator itself would have input here and output here. Here we're splitting everything so that we could test the modulator. And again, this is what a modulator looks like. So when then this is what a waveguide, the waveguide multiplexer, demultiplexers we were using at this time. This goes back to 2013 I do believe that we did this. And here we use rings. So the input signal comes along here. If it's at the right wavelength, it gets coupled up here, different wavelengths go in different ones. What doesn't get coupled transmits along here. So this is a De-mux of a multiplex signal coming in here. Everything works in reverse. So if we put 4 signals in here, they would go in and they'd be multiplexed going out this way. The purpose of showing all of this was that I started with saying that silicon photonics is a waveguide electro-optic device. If we look, everything that's on that chip, we have one of these at the input, we have some of these modulators in the middle, we have one of these flipped backwards at the output, we have one of these flipped backwards at the input, and then we have some detectors along the side. The silicon photonic chips contain only waveguides and waveguides with electronics on top of them. Okay, so to summarize this first part of what is silicon photonics, or what is it today, it's certainly the fastest growing market in optics. That 25% compound annual growth rate is very high, especially for something that's already past $1 billion market. It's an electro-optic waveguide technology, and it's of ever increasing complexity. Originally, we were talking about putting a modulator and maybe a modulator on a single chip, 1 to 5 devices on a single chip. Well, at this point now, as we saw, we're putting something like 300, 400 devices on transceiver chips, meaning that we've got more than 4 channels when all is included. On other chips, we're going up to 10,000 devices on a silicon photonic chip. But the last point here to be made is that this needs to be designed with automated tools, in part because of the complexity, in other part because of the EO devices and the detection devices that need complex doping, and the devices are small. So again, that's what silicon photonics is today. So let's move on to another topic here. Let's talk something about optical communication, because this is very relevant to what silicon photonics looks like today. The successes of optical communication are the places where we're trying to copy silicon photonics. We're trying to copy the functionality, but at an ever reducing and ever miniaturized scale. If we look at optical communication, a little bit of the history there, not much happened. There was a real need. People realized the need back in the 1960s that there was going to be a problem. The telephone network was growing. The size of the transmission structures, the cabling, the boxes that you needed to de-mux the telephone conversations were growing too fast. You couldn't fit them in trunk lines in cities. There was a lot of work during the 60s, including by Charlie Cow, who was at STL in Great Britain. Charles Cow received the Nobel Prize, I think it was in 2001, for his work on realizing that it was going to be possible to make low noise fibers, and that when a room temperature semiconductor laser came along, this technology was going to be unmatchable for what it could do, for the problems it could solve. And he wrote that paper. I think we wrote a series of them around 1967, 1968. In 1970, 2 groups, one at Lebedev Institute in Moscow, another group at the University of Illinois, demonstrated room temperature semiconductor lasers. The first ones in gallium arsenide. Progress came pretty rapidly to where they were semiconductor lasers, room temperature, also in indium phosphide, and then indium gallium arsenide phosphide, etc. The low loss fiber was Capra and Capron, Maurer, and Keck at Corning in 1970. That was less than 20 decibels per kilometer, but very rapidly, before this, it was about a dB per centimeter. Suddenly, there was a big change when they found out how they could use inside vapor deposition to get very clean fiber, and very rapidly, this went down to 3 dB per kilometer for multi-mode fiber, and soon after that, it went down to 0.2 dB per kilometer for longer wavelength single mode fiber. Bell Labs at first thought you weren't going to be able to use these things, that there needed to be more tests. You didn't know about the lifetime, but Bell South, part of Bell Labs, actually decided, well, what the heck, let's go ahead and try it anyway. In 1975, they put in a trunk line. It was a tremendous success. Everything functioned better than one would have predicted it would have functioned. And immediately, companies all over the world said, hey, we need fiber optic trunk lines. Our cities the ducts are filling up. We don't have any more room. So the United States and Europe started putting in commercial fiber optic trunks, mostly multi-mode by 1980. By 1985, single mode fiber technology was ready. Fiber long lines started to go across the world. I think already it was 1986 or 1987, the first transatlantic cable went in. And by the 90s, there were cables going across the Pacific and the Atlantic. And at any rate, now they bring Africa, South America. And we'll come back to this. In 1969, actually, before all of this, people were talking about integrated optics, but let's leave that for the next. Let's talk for the moment about fiber optics. So this is sent from the time that that first trunk line, or the first commercial trunk lines, were going in Europe and in the United States to the present. This is the capacity in bits per second of essentially a single fiber, one single mode fiber. And if we look up here, they drew a line, a Moore's law type line, that it would increase by 10 every 4 years. But at some point here, if we remember the center wavelength of 1.5 micron wavelength, the center frequency for that would be 2 times 10 to the 14th. This line goes right through 2 times 10 to the 14th, which would be hertz. So this line has gone through actually a bit per second, or I should say a bit per hertz. We're just barely getting to a bit per hertz. Of course, with high spectral efficiency coding, it's possible we could go beyond a bit per hertz in a fiber. This only went up to 2012. I think actually we were beyond that. Space division multiplexing has been not so interesting. This is a few years old. But if we look, this is one phenomenal rate where we started with rates that were on the order of tens of megabits, tens of megabit channel rates up to 100 megabits per channel rate when the first single mode fibers started going in. And now we're up to where we can actually put petabits, many, many petabits into a single fiber. You think about cables, they'll have 60 to 100 fibers. So we're way up there into the petabit type ratio when we have a full cable. Okay, and this is just to say the center frequency is 2 times 10 to the 14th. And if we look at this point up here already in 2000, what is that, 2012, 2013, we already had 2 times 10 to the 14th bits per second. We'd already achieved a bit per hertz on the center wavelength. So fiber capacity has increased, again, exponentially, much like the so-called Moore's law. But optical communication is point to point. The reason we talk about the channel capacity rather than some other measure like the density of components or such, is that the links are point to point. We have a laser, we have a modulator, we have a fiber, then we have a detector, and we have an amplifier. Now, these may be multiplexed. Maybe this laser gets demultiplexed. Maybe we have a lot of modulators. We put them through multiplexing into a channel. But a single channel of the optical communication system looks like this. And that single channel can only go so far because there's a loss budget. And this loss budget is pretty strict. What we've been doing is trying to drive the rate up. We try to modulate these lasers as fast as they can go. And then we try to use wavelength division multiplexing to put lots and lots of channels together. And that's fine, but the loss budget will only let us go such and such a distance for a single mode channel between amplifiers. That's circa 40 kilometers. It's very hard to go on a link more than 40 kilometers, and that's with no optical processing in the transmitter, no optical processing in the receiver. We're just connectorizing it. We're coupling into a modulator. We're coupling through a couple of connectors. And that plus a 40-kilometer channel is enough to use up all of the losses we can use up. Talking more about loss budget, a DFB laser, it would be a really powerful one to have a 4 milliwatt output. It's more like 1 milliwatt, maybe 2 milliwatts that you get out of most of these lasers that you use in the network. If you use an optical amplifier, you can boost that up a little bit, but generally you only do that when there are multiple channels, and you never get per channel over about a milliwatt or a couple of milliwatts. Even at 10 gigabits per second, if we look down here, this is the N0. This is the standard deviation of the noise in a receiver. This is the thermal noise due to the first resistor that you have to go through in the amplifier behind the detector. If we go down here to 10 gigabits per second, we've got about 3 microwatts of noise. If we look over here for non-coherent on-off keying, if we're talking about on-off keying, which is what we are in silicon photonics, if we come out here, we see if we wanted 10 to the minus ninth, we're at 15. Bit error rates used to be 10 to the minus ninth without error correction. But even without error correction, these numbers are like 10, 12. We'd be a very poor bit error rate to get down to 10. So even at 10 gigabits per second, we need something like 40 microwatts of signal. And that's with error correction if we want to get to 10 to the minus ninth. So that gives us a loss budget of like 20 dB, a factor of 100. And I'll show you here, demonstrate that that's small. The reason I go through this with such detail is the same loss budget is going to be true because we're using the same sources, because we're using the same detectors. The same loss budget is going to go over to silicon photonics. In silicon photonics, there's going to be more loss per connector. So just taking a quick look over here, a typical single mode link loss budget, you have a couple of dBs that you lose from the pigtail on the laser to the laser to the pigtail. So by the time, if you pigtail a laser, if you buy a pigtailed laser, good luck if you're going to get much more than 2 milliwatts out of it, no matter how strong the laser is. Connectors, you can get a connector that's 1 dB, but they get dirty, they get old. 40 kilometers at about 0.3 dB per kilometer would be 12 dB. You can get down to 0.2 dB kilometer for single mode fiber. However, that's uncabled. If you start putting it in a cable, it gets micro bends, the loss goes up. That's about 12 dB. We've got another connector before we go into the fiber pigtail, which is going to the pigtail to the detector is another 2. and we've already gotten to 20 dB, and we can't go any farther. And we can't put any other components in the transmitter. We can't put any other components in the receiver. We're very much tied to this loss budget. So what the point of all of this is that these the point of this is that the fiber optic links, yes, they have they've grown in capacity, and they're tremendously successful, and they're all over the world, and we have all kinds of undersea cables, but a link is limited to around 40 kilometers. You have to start putting amplifiers after that. You have to have power for those amplifiers. That's it. That's as far as you can go. There was a dream early on in fiber optics that we were going to do all kinds of optical processing. We'd be able to make optical computers. We'd be able to make all kinds of wonderful things where we could eliminate the electronics or move the electronics back. They haven't happened because we don't have the loss budget. The real advantage of the fiber optics has been pushing to the higher bit rates and not processing the signals. It's been carrying the higher bit rates that can't be carried by other signals, can't be carried by other media like wire, and carrying them in something that's light and small. So to say something about today's photonic links, optical communications today, they're still growing exponentially in capacity. Capacity just grows and grows and grows. We need more and more of these things. But these links are point to point. There's very little loss margin. And this is whatever we do. This could be cable distribution. This can be fiber optic cables for TV, CATV, whatever. All the links, the only way they work is point to point. Maybe you can have some fan out, but the fan out has got to be very, very small, and it cuts down your loss budget. All of these links now essentially are using wavelength division multiplexing in order to get more capacity per channel. So even though we have a single point-to-point link, we can send a bunch of channels on that. We can increase this to like 4 or 16 or even more channels than that. The other thing that I didn't really mention, but is a fact, is that time division multiplexing. We put together many telephone conversations that may be 64 kilobits per conversation, and then we time division multiplex them, and we stop at 25 gigabits per second. Past this, we start running into dispersion limit. Below this, we're limited by the loss budget. The loss budget, if we go faster, gets even smaller. With silicon photonics, we can push this to 50 and still be loss limited. Let's go on to another topic. Let's talk about integrated optics, and let's bring this right up to today's silicon photonics and how we got where we got. So let's start 1969 when integrated optics kicked off at Bell Labs. Let's talk a little bit about how silicon photonics came about. People talked about using silicon for a material all the way back at the initiation, but it didn't happen until 2003. We'll see why. Once it happened with a vengeance, with a fury, we could say, because as soon as this happened, it meant we could automate all of the processes. And then suddenly in 2014, as we saw from that market, 2014 was a massive inflection point where everything started taking off. And after we finish up with this historical part, we'll talk about technology, we'll talk about research. But let's find out why the research looks the way that the research looks, because it doesn't look like one might expect it to look. It's not processing, it's not active devices. What it is point-to-point links and really smart ways to use them. Here we go. Stuart Miller, this was 1969 at Bell Labs. This whole issue of the Bell System Technical Journal, these issues could sometimes be very, very long. This one was pretty long. There were a lot of papers. Stewart wrote his overview. Um, and that was, and then he had one or two papers in there, but there were probably 30 papers in there, some of them long, by Goel and Marcatilli and Marcuzzi, and the big names of fiber optics that later became big names of fiber optics were also part of this integrated optic effort over here. One of the important things that came out of this, there was a lot of stuff that never came to be, evidently. This was pretty early. This was before there was fiber optics. This was before there were room temperature semiconductor lasers. So this was very early. But one of the first things was that they looked at waveguides, just simple waveguides. And a lot of work was done, especially Dieter Marcuzzi did a whole lot of work on this, wrote a book on the theory of dielectric optical waveguides, which is still a classic today. I think that was written, I don't know when that was originally written, if it was before, I think it was after 1970, after there were fibers. I think there's a chapter in there on fiber optics. We talk about this here, looks like an etched waveguide. This looks like a silicon photonic waveguide. We talk about a parameter delta n, various people normalize or don't normalize. But let's say here it's n2 minus n1 over n2. It evidently goes between 0 and 1, at least for positive indices of refraction. Let's not get fancy here. So as this one gets greater and greater, as the n2 increases, this increases towards 1. Now, one of the first things we find out is that optical fibers had horrible loss when you try to increase N2. All optical fibers are very, what we would call very weakly guiding. This delta N is on the order of 0.01, 1%. The strongest multi-mode optical fibers, maybe this gets up to 2% or 2.5%. Single mode fiber, the kind that we use practically today, is around 1%. We call that weakly guiding. Weakly guiding, there's some advantages too. You launch a wave in here, it's essentially what we call a transverse electromagnetic wave, a TEM wave. It has transverse components of E and H, and it's pretty simple to analyze. Dispersion is reasonably low. It doesn't have a lot of components. That's, again, optical fiber, and practically all components. If we do ion exchange in glass, there were a lot of ion exchange in glass components for a while. Lithium niobate modulators, external modulators, are all in the so-called weakly guiding limit. With lithium niobate, maybe this gets a little bit bigger than 1%. Maybe we can get up to 5% if we're talking about ion exchange in glass, something like that. But what we talk about when delta N is greater than about 0.5 is a strong guide. The strong guide, among other things, what that means is we can turn this thing in a curly Q and it won't necessarily increase the loss. With an optical fiber, if we start bending, that radius of curvature has to be greater than about 1 millimeter. So more likely a centimeter, if you want to be certain you aren't going to increase your propagation loss. So you have to be very careful that fibers stretch out. So you can't put a lot of components, weakly guiding components, on a substrate. They'd go on and on and on forever because the bends have to be so small. If you get to the strong guide limit, though, you can put curly Qs and you can have almost right angle bends, not quite, but you can have all kinds of stuff on the substrate. But as I mentioned, originally back in the early days, if you tried to make these indices very different, it meant the materials were different. If the materials were different, there'd be lots of scattering at the interface, and that didn't work. However, silicon is a rather odd material in that it has what's called a native oxide. that native oxide is silicon dioxide, what we make glass out of. So if you have a piece of silicon which has quite a high index, 3.45, and you put it in a wet oxygenated atmosphere, you get an insulator glass, which is also sand. Um, Glass is actually sand that you heat up really, really high. You get this thing that has an index of 1.45 like glass. And it has a very low loss interface. It doesn't have a bad interface. It's the same crystalline structure. The structure hasn't changed too terribly much. So the delta N with silicon is near zero point 0.6. It is the first material that was strongly guiding. And if you can really cleanly put down that insulator layer on top of the silicon layer, for example, with techniques that we've come up with in intervening years with all we know about silicon, chemical vapor deposition and other techniques, these can be very, very clean interfaces, very, very clean silicon. A typical waveguide single mode in silicon is D by 220 nanometers. I mentioned that 220 nanometers is the upper layer. Single mode requires that D is less than about 500 nanometers. Just to compare this with an optical fiber, the optical fiber, again, the delta N is 0.01. If you have a typical waveguide, it's circular, it's around 10 microns or 200 times the size of a silicon photonic waveguide. You can't bend that optical fiber very much. We can kind of bend it down to a centimeter radius of curvature. The silicon on insulator, you can bend down to a 5 micron radius of curvature. Indeed, here are some devices. I wish you could see these scales better. I didn't do a good job. These are from my lab. These are various devices over the years for various things. This is a coupling grating. This is a 1 micron bar. So these grates inside the coupler are on the order of 200, 250 nanometers. This is 1 nanometer or 1 micron bar. This is a 5 micron radius ring. This here is an add drop multiplexer. Over here, if you're at the right wavelength, it couples out. If you aren't, it goes through. So it's a, I guess you could say, a pass filter or whatever. If you put a heater around the silicon, either that or if you put, for example, if you make it a PN junction, you make this a very high bandwidth modulator and a very small modulator. It's 5 microns or 10 microns all the way across. Over here, these tips are around 70 nanometers. Again, that's a 1 micron bar. What this is here is a one-to-all multiplexer, or actually fan out. If I put light in here, it will end up equally in all of these channels in every direction. And you can make them so that they're pretty near equal to within a dB or so. This, I think, is a 1 to 16. We've made, I think, 1 to 64, which has still been pretty good at mixing things up. Or you can, and again, this could be a multiplexed signal, and this has a rather wide bandwidth. So you could put a multiplex signal and put that multiplex signal to many, many, many other channels to put it apart. This is a ring type structure. It's like this one, but by changing the parameters on here, I can change the band pass. This is, we've talked about before, a demultiplexer. Again, these are 5 micron rings. This is 1 micron here. This is a 5 micron radius of curvature over here. So these are the kind of devices that silicon photonics allows you to make. Another one that it allows you to make is a modulator. This is not one of mine. I got this picture. Well, here it is. This is all the way back for 2010. This is the first 50 gigabit per second single channel modulator. This was an early one that came out from IMEC. This is a group in the UK. And at any rate, Silicon, originally people said silicon has no electro-optic coefficient. You'll never be able to make a modulator. But PN junction technology is really good. You inject carriers into a PN junction, you change the index of refraction. If you sweep those carriers out without any significant absorption, you can still change the index of refraction in a big way. It turns out that silicon photonic modulators are faster and better lower loss than other kinds of modulators, although at first people thought it couldn't. They are. So at any rate, another advantage of silicon photonics is that Moore's law. Here we look at Moore's law, which tells us that the number of transistors in a CPU or on a chip, this should probably be, has increased since 1965 when Gordon Moore noticed that everything was increasing exponentially. That's been going on for almost 50 years. It's starting to trail off a little bit. This is the size. This is what's called the standard node size. In order to get these more transistors, we've had to go to a smaller and smaller gate length of transistors, of CMOS transistors. So this is saying the size scale has gotten longer, the minimum feature size. Why do I bring this up? Well, let's take a look. Technology nodes. So as new foundries come out, as years go on, 1971, the minimum feature size was 10 microns. 2020, it's 5 nanometers. Each one of these, though, requires either a complete refurbishing of a foundry or a new foundry. And these are the nodes, they're standardized across the industry so that everybody's making the same type of transistors. They can all be interchangeable. That's what's driven this Moore's law. Well, if we look along here, we get up to, as we mentioned, silicon photonic waveguide needs to be less than 500 nanometers. When we got to 180 nanometers as a feature size, we could kind of make a 450 nanometer waveguide. Kind of, it was 2.5 feature sizes. They weren't very good. By the time we got to 90, they were pretty good. At the 90 nanometer mode, you can make good silicon photonics. You couldn't back here. You couldn't make a single mode waveguide. All of a sudden up here, we could take a CMOS foundry, and with that CMOS foundry, we could make silicon photonics. Now there's a 5 nanometer size that we've gotten down to feature size. Well, we can use a foundry that was built in 2003 that has become much, much less valuable because of all the intervening nodes. You can't really do a lot of really interesting CMOS in that foundry, but you can do silicon photonics. And this has been a major driver of silicon photonics. Once we got to the 90 nanometer node, we could make the waveguides. Now, one of the other papers, this actually was a paper that was published in another journal. This was Physics Review Letters, if I'm right. Reinhard Ulrich and P.K. Tien. What this paper, they also had a paper that was in Stuart Miller's 1969 BSTJ, Bell System Tech Journal. They published another much more scientific paper. Kind of the idea of that paper was they were saying, boy, it's hard to couple into integrated optics. This was weakly guiding optics. You had to use a prism. This prism, you had to have 6 degrees of alignment. You had to have this angle, had to be just right. The prism had to be aligned with the waveguide. And if it were a surface waveguide, well, then you wouldn't have to laterally align. But for a surface waveguide, you also have to get the beam to stick on the surface waveguide. And this would be to couple light in. You'd use a prism like this. You could cut the prism off and you'd couple into the waveguide. with a prism on both sides, you could find out what the propagation characteristics were and find out whether or not it was single mode or multi-mode. But boy, this is a hard way to couple in. And that was one of the ideas of the paper. You actually needed a thing up here where you actually bent the substrate in order to get coupling. And these were the original couplers, the first ones that you could use for integrated optics before we got to end fire coupling. This paper, if we start talking about coupling now to strong guides, these fibers are actually not really to scale. This core is about 10 microns, and these grating couplers in silicon photonics are about 10 microns until 2014. This is about the only way that you could couple into a silicon photonic guide was through these grating couplers built into the surface. If this were the right size, this is actually 125 microns. It would be much, much bigger. You have to put the fiber core this close to one of those and the output fiber core. Coupling out is easier than coupling in because you have to find the waveguide. These things here had a minimum of 3 dB per channel in order to couple light into the silicon photonics. So the loss budget is worse in silicon photonics than in fiber optics. Here's an end fire coupler. You can also try to couple from a fiber into silicon photonics. This, again, this is 10 microns. This is only about 20. This actually goes out is 100 or 125. This is much, much bigger than that. But this kind of gives you an idea of the scale. Is just going the 10 microns to the half micron down here. That's a factor of 20 already just to get into the silicon photonics. This is what this looks like. You can't get that fiber. Actually, this shows it getting really, really close. Good luck. This is a microscope objective, which is hooked to a fiber, which is focused down to try to go into the silicon photonic chip. One of the reasons we couldn't put the fiber all the way down is this is a modulator. The modulator I showed you earlier, we have to put electrodes on that modulator, and we need this big jig because we're putting microwaves into that modulator in order to modulate it. Well, here we can only get one side of the modulator. We can couple in light, we can couple in microwaves, but we can't couple in and couple out. We have to have a detector on chip to be able to tell us whether or not it's modulating. We can't even go in and out of a chip because this thing is so small. And the coupling is so hard, in part just because of the size of things, not even the alignment problem when you get all of these things lined up. This is, Tyndall is a packaging house, or it's actually an institute in Ireland. Peter O'Brien has a big group there, a big packaging group. He's been working with IMEC, the Belgian foundry, since 2007, 2008. He's also been working with AIM, the American foundry, on packaging techniques. And he's been coming up with standardized jigs so that if you make a component with that fits one of his jigs, then the measurements are pretty easy to make. If you make a component that doesn't fit his jig, you're on your own and you probably can't do it. And I guess the bottom line of all this is design and testing now require foundry automation. Silicon photonics is what we call fabless production. We used to, when we'd make integrated optics or we'd make fiber optic experiments or something else, we'd work in our lab, we'd make things, we'd put together measurement jigs. At this point, we sit at a console, we design things, we design them to certain specs, and we try to get the foundry to make the measurements, or else we try to make them make only certain devices that'll fit jigs that we've bought from people like Tyndall or that we've copied from Tyndall. Everything in silicon photonics requires foundry automation. The other thing about silicon photonics was the cloud, which was born around 2000. It originally used optics to interconnect all of the processing power inside of it. This is a warehouse scale, actually 2 warehouse scale computers. It requires a 250 megawatt power station, a third of the power for the cooling towers. A third of the power is used for the telecom lines coming in and out, and a third for the computers. The original data centers, they haven't changed too much in size. They have up to 100,000 racks, but the original ones were using 1 gigabit per second VCSELs on multimode fibers to hook together the racks and to go across the data center. This is telecom in, telecom out. And this was so slow that already by 2013, it required a major change. There were these aggregators in here in order to accommodate those 1 gigabit per second with faster stuff coming out from the core. Now all data centers go to this so-called 2-tier leaf spine network architecture. And just to get to this is very important to silicon photonics. The optical part of the network is all network transceivers. Let's take a look at that. And again, these servers, each server has a gigabit Ethernet card. So we have fiber going into these gigabit Ethernet card. Sometimes the rack is done with gigabit copper because the rack may only be a meter high and kind of get by, but everything else has to be fiber. Let's see what that looks like. So that's something like this. We have spines up here. Someplace in here, the lines can come into the spines and go into the center. But what happened around 2014 was that little transceivers, if you had little plugins to the spines and little plugins to the leaves, if you had these little transceivers that would plug in, you could make everything modular. However, these transceivers, 1 gigabit wasn't enough. They started at 10 and very rapidly went to 25 as a standard. And after that, they started to multiplex to 100. So the customer problem in 2014, this is another data center. Again, you've got cooling towers. This is in the north of Sweden. It's cold in the interior of Sweden, so you didn't need as much cooling for this one. These are what the racks look like. And again, there could be 100,000 of these racks inside of here, probably are. 100,000 is about all that you can get in with 250 megawatts. And here are all of the connectors coming out of the gigabit Ethernet cards. And in 2014, the problem was to come up with 100 gigabit per second transceiver that went in one of these little packages that you could plug in like that. And they had to have this 2 kilometers was overkill. I think this is down to 100 meters or something. You don't need, this isn't 2 kilometers long. But at any rate, this was what the problem was. And we've already said this was the solution. And as it turned out, the solution, as soon as you needed multiplexing, you needed silicon photonics because it was the only way you could make the multiplexers small enough that you could actually multiplex signals onto the fiber. So this was when silicon photonics took off. The other thing is, as I showed back here, sorry to go back and forth, but every one of these leaves needs one, and every one of these leaves goes to a rack, and there are 100,000 racks. So you need kind of minimally 200,000 transmitters, 200,000 of these transceivers per data center. There's something like 200 data centers. We're talking about millions and millions, tens of millions of transceivers. And there, at one point, were 23 transceiver companies. They've consolidated a little bit since then. And this is what drove this market. We've already talked about this market. And this is what's still driving it, is that they have to change these transceivers about every 18 months. So there's still a tremendous market. Data centers are being built, more transceivers are going in. People are finding other ways to use transceivers. Again, 200 data centers, 100,000 racks per data center, 2 TXs per rack at $500 a transceiver back here. Now the transceivers are down to under 300, but still, um, there are a lot of them. So today's silicon photonics, an exponentially growing market. It allows point-to-point CMOS interconnection, but it's going to be loss budget limited. The losses per facet are higher than with fiber and laser because they're strongly guided. We're coming to see increasing density and fan out of WDM channels, which means that the length that you can transmit may be smaller, but we're doing more and more on chip or on board. So we're going smaller distances. We can miniaturize and get a little bit more fan out, but we're still limited very seriously by that loss budget. And we can go up to 50 gigabits per second. Let's talk a little bit about research directions and issues. I'm coming to within the last 20 minutes, 15, 20 minutes. So I don't think I have more than 15, 20 minutes of material here. We're going to talk about higher complexity. We'll talk about high performance computing and using active sources and using miniaturization, or what are the trends for miniaturization. Here, the research area is COMB for active sources. Here, the research directions, inverse design for the miniaturization. Here, this is from John Bowers at UCSB. This goes back to, I think I had written it down someplace, 2017, 2018, I'd be pretty sure. This is an 8x8 transceiver, so 64, it's got a crossbar with 64 elements in it. So you have multiplexing of 8 coming in and multiplexing of 8 going out, where you can completely interleave all of these. So this was, I think John actually made this to show that he could make it and to show where you could go with miniaturization. He had some trouble testing this. He could only test one channel at a time because it didn't fit any standards at the time. It was pushing ahead. Again, the chip is 1 by 1.5 centimeters with 2 fiber IOs, but it has 8 transceivers and it's 8 channels per transceiver. So this is about where we can go. The highest complexity yet was this crossbar switch over here, where somebody made a 50 by 50 crossbar. That means it had 2,500 interconnection channels in it, 2,500 crossovers, and these boxes are probably the crossovers. And this could be for multi-chip optical interconnection, which could be used in artificial intelligence. We can take a quick look at that. It's a very interesting application. So this is an accelerator, a GPU and accelerator, an NVIDIA GPU accelerator. Here it is on a package. You can buy 4 of these and put it around a CPU, and you get the state-of-the-art AI device that goes on a little board. A problem that you run into is that the bus is at 2.4 terabits per second inside this NVIDIA GPU. And you could put a chip over here and have 4 of these things coming off. The problem is that's as much as you can do. At that point, you can't go any farther. That's the biggest AI machine pretty much that you can make. You can reprogram it to get some more AI power out of it, but you've pretty much exhausted copper interconnections. Because if you go any farther, it slows it down too much. You can't go from step to step. You need lots and lots of steps in these AI things. If you're using convolutional neural networks, you need lots of stages, but you need lots of crossbar interconnect when you get to the inner layers of the convolutional neural network. And again, we're talking about the cut through bandwidth of this is like 120 terabits per second. However, silicon photonics could be used underneath the chip as kind of a board level to hook together all these GPUs with the central, and you could expand the size of the AI network greatly. You could expand it to a board level by doing that. Again, we can go to 50 gigabits per second, as we know, with silicon photonics. 2.4 terabits per second, the kind of bus rate. If we wanted to open that bus and share that bus across the CPU with 4 GPUs, we'd need something like 48 modulators and 48 detectors for each line. But again, you can see doing that. That can be done, as we saw, somebody's already demonstrated a 50 by 50. So we could make this kind of 48 by 48 pretty easily on silicon photonics. And these are the kind of applications that people are starting to look at. A big problem with all of this would be just the sheer number of lasers if you were using a laser per channel, like 48 times 48, and you're going to start needing hundreds and hundreds of lasers. All those lasers need power supplies. They all aren't the same. You'd like to minimize the number of sources, de-mux the sources, maybe put a few optical amplifiers in there, but have a handful of lasers and a handful of optical amplifiers off chip in order to do this. And that is a big research area. And I'd had it all the way back here. You can use a DFB-based comb. Let's take a look at what one of those might look like. It might need an optical amplifier in the package as well. Here was an early one. This actually was using, this came from Karlsruhe. This came from Karlsruhe in 2018. One of the first people to use a comb. And here they have an optical amplifier. And they're doing this off chip. They have a silicon photonic chip with a polymer implant in order to give more oomph to the modulator. And what they do over here then is they have a 40 gigahertz generator, and they're able to generate these lines spaced by 40 gigahertz using one source, one DFB source over here. These things in German take me a minute. All the initials are in German. But here we've got 5 channels out of one source and one out of one optical source and one microwave source. And these are spaced so that you could put 40 gigahertz, 40 gigabit modulation on each one of these, and they'd fit perfectly. They fit one to the other because there's fixed relation between them. So this was Lin et al. At at Clio. This was a OPEX article. This was at Clio. So this is the output. This one here was using a polymer modulator. This one here used only a silicon photonic modulator. And again, the one that got 4 channels. Oh, over here, I see, excuse me, I missed it. These are 40 gigahertz. But if we look at this, we've got more like 8 channels over here with the extra oomph from that. But that was just that these were early demonstrations. You don't need polymer to get more channels. Over here, there's this demonstration here, which used a notched filter. It used, again, a microwave source, but drove it pretty hard at 10 gigahertz. And it didn't look too smooth, but when you put a comb filter source on it, comb filter on it, put on a ring filter on the comb signal, what we found out is we get something like 37 lines that are all within a couple of dB of each other. So you can talk about more. I've seen people get up to 50. I couldn't get a good picture of any of them. Some simulations I wrote or that we ran with one of my colleagues, we were able to show that we could get 64 pretty easily matched. We haven't made that device yet. We're planning on making that device. That device, again, was something along the lines of this, although it had a double Mach Zehnder instead of a single phase modulator. So this is a growing area of being able to use, again, a single DFB laser, and then maybe we can use a semiconductor optical amplifier. People like Bowers has been using semiconductor optical amplifiers in devices that he's been making. So I have good confidence that they're going to work and they're going to fit in these packages, in these interposer type packages. The other problem we have is miniaturization. This is an arrayed waveguide grading. If we really want a lot of channels, arrayed waveguide gratings are a much better way to get them than rings. If we use rings, they don't have a fixed relation. Those comb generators have a fixed relation, a fixed spacing between channels. We can get that fixed spacing if we use an arrayed waveguide grating, which has an input, expands it out, puts in delay lines, then recombines these. You can either put in one channel and get out 512, or you can put in 512, and if they're spaced right, get out one. So this is a 1 to 512 modulator, but this requires 176 square millimeters in order to make it, and that's too big. That's bigger than most of the chips. Most of the chips we're talking about, right, are smaller than this multiplexer itself. These don't scale very well. What can we do about that? Inverse design is just getting going. Inverse design, instead of using a physical principle, you use a layout, you write Maxwell's equations, just like you do in some of these brute force solvers that are being used now, and you put on some optimization criteria, you let it optimize. Here we have a three-channel multiplexer over here, and this three-channel multiplexer is 4 micron by 4 micron. If you tried to scale that using the scaling laws, you'd find out that you could make this in like 50 or 100 microns squared. You could reduce by many, many orders of magnitude, 3, 4, 5 orders of magnitude over what you can do with arrayed waveguide gratings. The surface of this is only being scratched. We're just getting there. There are groups doing this at Berkeley. There are groups in China. There are groups at Princeton. A group at Michigan that I'm working with is starting to get into this. We're starting to look at, can we scale this up to large numbers of channels and still have this advantage? This seems to, we've got these with like 6 channels coming out. I didn't have a good picture of one that seemed to greatly violate the diffraction limit by quite a large amount. And we don't know why, because again, if you look at this, you can't make hide nor tail out of this pattern, yet it works. It works quite well. The crosstalk here is very low, minus 20 dB, and the losses are very low also. These are matched to well within 1 dB at the output. The other thing that we can do with this, and actually more people are doing bends and crossovers than are doing muxes and demuxes. One of the problems that we've mentioned before is that, again, with fiber, you can't bend it very much. With integrated optics or with silicon photonics, you can bend things very sharply, but when you start having problems, you have problems. And the bends don't match what are in most layout routines in CMOS layout software. So you can't do a big layout. The layout just fails to work. It will give you bad channels. It will give you other problems. You can't minimize the layout size. So there still are problems with going to completely automating everything. But one of the things we can do is lay these out in rectangular networks and then put in right angle bends into these things. And these right angle bends can be very low loss. They don't have much loss at all. It's down to, yeah, um, output at the bend, uh, reflection from the bend. These are very, very down with respect to 1. So these are like down minus 25 dB. So the losses are down to like fractions of a percent at right angle bends, which is a great advantage. Again, this is a paper from Nature Science Reports. This is a Chinese paper. The other thing that can be done is crossovers. We talked about doing 64 by 64 crossbars, and you have a lot of channels. That 50 by 50 crossbar was 2,400 channels, 2,500 channels that had to cross over each other. Crossovers, you can get low loss in silicon photonics, but it's hard work. People have to optimize them, and it has to be done by hand and by trial and error. Again, these things over here, you're getting the losses down at design wavelengths well below 20 dB, so down below 1% loss. So if you could start doing these with 64 channels in and 64 channels out in tiny distances, we could start talking about really minimizing layout. And this again is another one of those design type problems. This is not like the physical type design that we've been doing in the past. This is working on a computer and working with design software. So it's a change from what we've been doing in optics previously. This whole fabless type work is completely different. But at any rate, let's summarize at that point. I'm running low on time. Silicon photonics is shrinking to solve interconnection problems at ever smaller scales. The state of the art requires automated design and testing with foundry fabrication and perhaps foundry testing as well. Layout requires new tools, but options are appearing. Again, things such as this inverse design. The foundries are starting to have their own inverse design groups inside the foundries in order to see if they can make standard components that people can pull down from process design kits. Sources and amplifiers remain problematic and likely will remain problematic for the conceivable future. We haven't been able, no one's been able, especially to get to do heterointegration of gallium arsenide or indium phosphide on silicon. I don't see that happening, especially soon. We're probably going to have to work with these kind of systems in package and systems on board that have been the standard of electronics, CMOS packaging, really since the 90s, since we started to see PCs and other small electronics come out. And we're probably stuck with that for some length of time into the future. So with that, thank you for your attention.